This is the first video that I'm doing for the Math 20 class, and I'm going to start with section 4.5 because that's where we are. The whole reason behind doing this is because we're a little behind on schedule, and I thought maybe if I made some videos for the class, it might speed things up for us and be beneficial for the student who needs to get a lot of repetition on the lectures. So we're going to give this a go and see how it goes. So this is section 4.5. It has to do with scaling, proportions, and units. By the time we're finished, hopefully, the student will be able to scale up and scale down to solve problems, use scale drawings to answer questions, solve area and volume problems when units change or when the scale changes. When two ratios are equal to each other, and remember, a ratio is just nothing more than a different name for a fraction. If something is represented with a numerator and a denominator, it can be referred to as a ratio. And ratios are generally used when you're comparing two things, men to women, apples to oranges, and so on. When two ratios are set equal to each other, then we say that they are proportional. When we were working with fractions before, and we had a fraction like 2/3, and we took 2/3 and we changed it to an equivalent fraction, and remember there are infinitely many. Let's say that I multiplied top and bottom by 5, then I would get 10/15. And we would say that these fractions were equivalent to each other. We never used the word proportional, we just said that they were equivalent. Well, now when you get a fraction in terms of a ratio and it's equal to another fraction in the form of a fraction and referred to as a ratio, we say that these two things are proportional to each other. So let's see what that means. We can say that A over B is equal to C over D. If that's a true statement, if we really know that that's a true statement, then we can say that this is a proportion. The ratios A over B and C over D are equal to each other. They're equivalent to each other. An example of a proportion, just like the one that I did over here, could be 12 over 18 is equal to 20 over 30. This guy, if we knock that down by 6, 6 goes into 12 2 times, 6 goes into 18 3 times, and then we can reduce the fraction on the right by 10. 10 goes into 20 2 times, and 10 goes into 30 3 times. And they all boil down to exactly the same fraction. Common uses of proportions are when things are being scaled up or things are being scaled down. For example, if we have if we're interested in a map of Oregon, you can't go walking around with a map that's as large as the state of Oregon. That would be ridiculous. So you, in this particular case, take something that's very large, the map of Oregon, and reduce it down. And if whoever manufactured it did a really good job, then the map that you have in your hand would be nothing more than a scaled down version of the original, and they would be proportional to each other if you were looking at the distance, let's say, between a couple of different places. Likewise, so this is scaling down. Likewise, if you were taking a class and you were learning different parts of the human heart, why, it's a relatively small organ, but if you wanted to learn all the different parts, you would probably want that scaled up, a larger picture of the real deal. And that would be proportional then to what the heart really is. One of the things that we do all the time is with photographs. We'll take a photograph of something and we'll shrink it down and we'll make it larger. We do that all the time on our computers and on you guys who have iPads and iPhones and all those other things. We're constantly making things larger and making them smaller. It's easy to understand how scaling up and down can affect lengths. An object can be twice as long by just simply multiplying it by 2. So if I started with this object and I just wanted to take its length and double it, well, then this is basically what I'm looking at. Or I could take a picture of a mountain, let's say some guy up on a mountain, and I want to scale down its height. You know, it's going to look like this. It's going to be shrunk down and squished down like that. And I'm just basically dividing its height by 5. But when we do scaling properly, we want to scale down all of the dimensions. In other words, you know, when you're looking at something on the internet or on your phone or whatever, and you've got a picture of somebody, and you put your cursor over the edge of this picture. If you're over here in the corner, you're going to see a little double arrow. If you're over here on the side, it's going to look like this, and if you're over here, it's going to look like that. And if you wanted to make this thing larger, you come to the corner and you drag it over. And as long as you are in the corner and drag it over, then it grows proportionally to what the original figure looked like. If you drag it over here, it's going to get all squished down and look funny. And if you drag it over here, why, then you're just changing the height and not changing the width, and it's going to look really skinny. Scaling, generally speaking, should affect all of the dimensions, although it could affect just the length or just the width. Scaling up and down affects length, but it significantly affects the area and the volume and in different ways. And this is important for you to understand. Sure, I could take, you know, like I did up here on this rectangle, I could just take this and double the width, and, you know, that's what it's going to look like. But what happens with the area of the figure that we're starting with? So if in this figure I originally started with an original width of 2 inches, and we'll call that 2 inches, and an original length of 3 inches, I could double the width, so that's going to be 4 inches, and I could double the length, and that's going to be 6 inches. But what happens to the area? This is really interesting. Well, what's the formula for area of a rectangle? Well, that's just area is equal to length times width. So if I originally started out with 2 times 3, the area of this thing would be 6 square inches. 6 square inches. But by doubling the width and the length, I end up with 6 times 4 over here, which is 24 square inches. Now you might think, wow, well, how'd that happen? All I did was double the dimensions. Yeah, you did double the dimensions, but the deal is that you doubled each one of them. You've got 2 times here, and you've got 2 times here. You got 2 of those 2 times, and that's why in this case this area ends up 4 times as large as this. 4 times as large. So if you're doubling the dimensions and still looking for the area, this is what's going to happen when you're doubling. Because he appears twice, you end up with an area that's 4 times. If I were to multiply the length and the width by 10, here's my original, and I do length and width by 10, that's 10 squared. That means my area is going to be 100 times my original. And we're getting a little long on this video, so we're going to go ahead and stop this, and then I'll continue with the next video.